In this video, I am going to explain some very important term, and it is about the oxides of nitrogen. So, nitrogen, it is very anomalous element, and so it forms large number of oxides under proper condition. This. Now, nitrogen is highly stable. It is inert element, and it becomes active only at elevated temperatures. Only at elevated temperatures, it forms variety of oxides, and it is in different oxidation states. And first, oxide is NO. It is nitric oxide. It is nitric oxide. Now see, here this oxygen has valency of 2 minus, so here it will have 2 plus. So here nitrogen has oxidation state of 2 plus. This is nitric oxide. Nitric oxide, it is formed by the oxidation of the nitrogen gas in the internal combustion engines, or the engines which runs on the any fossil fuel, and so this is there. Now this is colorless. Point is, it is a colorless. It is a colorless gas. This is important point to note, that nitric oxide, it is a colorless gas, and it is it is having neutral character. Colorless and neutral character. It is neutral in nature. So this is there about the nitric oxide. Now coming to NO2, nitrogen dioxide. Now as here oxygen has 2 minus, so here it will be total charge will be 4 minus, so here it will be 4 plus. See the variety in the oxidation number. And so this is it is having the brown color. It is having brown color, and it is acidic. This is important to note. Brown color and acidic in nature. And how it is obtained, or how it is produced? It is produced by the action of either nitric acid on the metals, or by the decomposition of nitrates. When any nitrate is decomposed, like if we take the lead nitrate and we heat, then there is formation of lead oxide plus NO2 plus there is O2. So this is there, or it can be there. So see, brown color and acidic. See the variation. This is colorless. Nitric oxide is colorless gas. It is neutral. Nitrogen dioxide, it is brown colored gas. It is acidic. It means it is nitric oxide. It is neutral, brown color, and also it has pungent smell. This is important to know. It has pungent smell, and this NO has nothing like this. Now the third is N2O3, dinitrogen trioxide. Now it is also formed by the different conditions. Under highly specific conditions, we don't have to know this. Here see the valency. So oxygen, so see here total charge is 6 minus. So here it will be 3 plus on total. So this is it has 2 plus, here it is 4 plus, here it is 3 plus. So now about the properties, about the feature, that it is important to note that it is blue. It is blue solid. Very important to note. This dinitrogen trioxide. This is dinitrogen trioxide. It is blue solid. No doubt it is gas, but it has very important point that it has blue color at very low. All the oxides, they exhibit, or they can be studied at very low condition, and so this is there. And it is also having the acidic nature. So see the variety, it is blue solid, it is acidic. So this is about some of the important oxides of nitrogen. Oxyacids of nitrogen. So it's very simple. Oxo means there is presence of OH group, and so oxyacids or oxyacids are the acidic substances. Acidic substances, they are acidic in nature, formed by the dissolution of oxides of nitrogen. You know, oxoacid can be of any non-metallic oxide. Any non-metallic oxide when it is dissolved into water. Oxide nitrogen on dissolving in water. So it forms large number of oxoacids, not nitrogen but different non-metals also, and the important ones are HNO3. You know those things. HNO3, it is nitric acid. Then HNO2, nitrous acid. These two are very important compounds, oxoacids of nitrogen. NO, nitric acid, NO2, when it is dissolved into water, there is formation of HNO3. Nitrous acid is also produced in such similar reactions, either by the disproportion reaction of HNO3 or similar reactions. Now, these are some of the important oxides of nitrogen. So we have seen here nitric acid and nitrous acid. Then we have this HNO4. HNO4, it is per nitrous acid. Per nitrous acid, HNO4 per nitrous acid. Then the other one is, it is also highly unstable acid, and it is H2N2. It is H2N2, H2N2O2. This is, hyponitrous acid. So, except this HNO3, these all three, they are unstable. They are unstable, and because the bonds are very weak and they undergo, decomposition reaction. Nitrous acid, it cannot be stored. Nitrous acid, it cannot be stored, and nitrous acid, it is prepared in situ whenever it is required in nitration or some other reactions or diazotization. This nitrous acid is required in diazotization. Diazotization means the addition of nitrogen in the conversion of aniline into benzene diazoxide chloride, that is diazotization. So it is prepared in situ. We say it is prepared in situ. In situ means where it is required. So nitrous acid. Now this nitric acid is the only stable oxyacid of nitrogen, and they are highly unstable. And nitric acid is also highly reactive. It can oxidize other elements, rather it can oxidize metals as well as non-metals both, and because it wants to have the stability, so it oxidizes others and it is reduced. So this is about the oxyacids of nitrogen. Now I am going to explain nitric acid HNO3, and first we'll see the lab method for its preparation. So laboratory method. In laboratory, it can be prepared for experimental purposes in very small quantity. It is prepared by the action of concentrated sulfuric acid on calcium nitrate. This calcium nitrate solid, it on treatment with concentrated sulfuric acid, or you can say oleum. Oleum can be taken H2SO7. So, and it is heated. It is heated in glass retort. Retort is, very special type of glassware, and it is there. Just we'll see after, some time. So there is the formation of HNO3 gas, and there is calcium sulfate. So then HNO3, the fumes can be condensed, but rarely it is used. Actually, glass retort is basically, it can be of glass, it can be of any metal. So similarly, it is this type of vessel, and it has a mouth here like this, and then there is this type of structure, and it is there, and here there is a lid. This is the lid, and it is heated, and here there is a stand. So this is there, this is the retort, this is glass retort, and so then there can be condenser, and so anything can be there. So this is about the retort. Now coming to commercial method or industrial method. So commercial or industrial method, it is prepared by Ostwald method. It is prepared by Ostwald method. It is prepared by Ostwald method, and in this method, the ammonia is the starting material. Ammonia is the starting material, and ammonia gas is oxidized to NO2. Ammonia gas is oxidized to NO2 under highly specific condition, and so it is oxidized by platinum gauze. So there is the requirement of ammonia gas. Pure ammonia gas is taken, ammonia gas, and then there is the requirement of oxygen, and there is the platinum and rhenium catalyst. Platinum and rhenium, they are highly stable metals. Platinum and rhenium, they are very inert metals. Very high temperature is required, and it is around 900 Kelvin. 900 Kelvin temperature, it can be 1000 as well. So it is there to convert into oxide of nitrogen, that is NO2, and then ultimately it is having some pressure also. So there is some atmospheric pressure, around 300 atmospheric pressure, and so then there is formation of NO, and then there is formation of S2 also. Then later on this nitric oxide, it is again, it is oxidized to NO2 gas. So this is, you can write here also, and so this is the first way to preparation of NO2 gas. It is first step. Now in second step, there is the dissolution. Dissolution of NO2 in water. Nitrogen dioxide is dissolved into water. There is a dissolution into water, and then NO2 gas. Actually, it is bubbled. It is bubbled into water. So there is the formation of HNO3 aqueous, and here it is dilute nitric acid. This nitric acid is here. The nitric acid is dilute. This nitric acid is dilute solution, and it is dilute solution. It is around 40%, depending on the condition. So this is the average condition. It is around 40%. It is around the 40% solution of nitric acid. Then it is further concentrated. It is further concentrated to get the concentrated nitric acid. Now its concentration. So its concentration. So around 40% HNO3. It is dehydrated by volume. Dehydrated by volume means H2SO7, or you may say concentrated sulfuric acid. So sulfuric acid, it is having very strong tendency to dehydrate anything. So as it contains lot of water, so volume or concentrated sulfuric acid, when it is heated at high temperature, and so when the nitric acid, it is kept in a special type of vessels, as a result it removes the moisture, and as a result there is formation of HNO3 concentrated. So there are different methods. So actually there is the cascade method, and cascade method, and cascade method actually it is having lot of vessels. It is special type of chamber, chambers, and suppose in the chamber there are some steps like this. Steps are there like this, and here there is the vessels. There is the vessels of this, and the sulfuric acid is present, and then there is the dehydration, and so this is about the preparation of nitric acid. So after preparation we have to see the properties. So it is colorless. You have to keep in mind it is a colorless, thick, means dense liquid. It is sticky liquid in pure condition. It is colorless. In pure condition it is colorless, thick, dense liquid. Sticky liquid, you can say it is sticky liquid. Now second point, on long storage or storage under ordinary conditions like the bottles in laboratories, or it is not properly capped, just the stopper is put over there. It undergoes self-ionization. It undergoes self-ionization or self-dissociation, or simply you can say dissociation reaction, and acquires light yellow color. This is, very important point. Light yellow color. This is self-dissociation. Only about the concentrated. I am referring to concentrated HNO3. So when there is the concentrated HNO3, then it undergoes dissociation and there is formation of NO gas and there is the water. That's why, children, you have to keep in mind in laboratory the nitric acid bottle. This is very important point, that in labs the concentrated HNO3 bottles are having light yellow nitric acid, because NO2, it has brown color. It has brown color. Even if it is produced in a very small quantity, so it will be dissolved, and as a result, it has light yellow color. So this is very important point to note, and it is due to the dissociation or self-ionization, and so it requires yellow color. Now coming to third property, it is very strong oxidizing agent. It is very strong oxidizing agent, and it can oxidize metals as well as non-metals, and can oxidize metals and non-metals easily. Metals and non-metals easily. That is, metals are converted into nitrates. Metals are converted into nitrates, and the conditions are under different there. So if you take the copper solid in presence of nitric acid, here if you take the dilute, so there is formation of copper nitrate, and in addition, there is the liberation of nitric oxide gas, plus there is nitrous oxide gas, plus there is, now here there is no colorless in when there is the dilute HNO3. But when we take this copper and there is the concentrated, then here the product is same, and we get nitrogen dioxide, and there is, so thus here there is a brown gas. This, but here there is, if it is the dilute, initially there can be nitric oxide, but later on it may react. If we keep for some time, then it reacts and then form the, because combines with oxygen. But initially it will not have it. You have to keep in mind, when we treat copper metal with dilute HNO3, initially there will be no brown color, but after some time, after some reaction, then it requires orange color. But initially when you take nitric acid concentrated, then immediately we get the NO2 gas. Now coming to some more metals, non-metals, like if you take zinc again on reaction with HNO3 in dilute condition, salt will be same. There will be zinc nitrate plus H2. Again there will be formation of oxide, and here there will be dinitrogen oxide, nitrogen oxide. But when we take zinc and this HNO3 concentrated, so there will be zinc nitrate, here there will be zinc nitrate and plus water, but here there will be NO2. Now see the condition. Here oxidation state is something different. Here oxidation state is something different. Here, it is 2 minus, so it will be 1 plus. Here it is, this 2 minus, and here there will be 4 plus. So it is there. So you have to take. Nitrogen, anomalous in character. So here, this is there. Now coming to with non-metals. So in non-metals also, it is able to form some compounds here. Now here, I have written very important reactions. Now here, these reactions are very important. Reactions of nitric acid concentrated with iodine. When we take iodine solid and take nitric acid concentrated, in all the conditions you have to heat. In case of metals, it is not necessary to heat. Metals reaction take place strongly when we heat, but non-metals it is mandatory to heat. So when you take the iodine solid on treatment with nitric acid, there is formation of HAO3 iodic acid, and again NO2 is formed. So this nitric acid, it oxidizes others and then it is reduced to form the water. Similarly, carbon or graphite can be taken heating. So all are concentrated. You have to keep in mind, all are concentrated and they have to be heated. So there is formation of CO2, water and this NO2 gas. See, the oxidation number of nitrogen has been changed. When you take nitric acid concentrated, then there is formation of NO2. See, in all the cases, there is formation of NO2. The oxidation number has been changed. In case of concentrated dilute, it is NO. When we take the sulfur, S8 means elemental sulfur, again 48. Very large amount of nitric acid required, and then the formation of this sulfuric acid, NO2 and this water. So see the condition. In all the conditions, water is same and oxides are also same. So this explains the point. Last, then phosphorus, elemental phosphorus. It can be yellow phosphorus, it can be white phosphorus, it can be black phosphorus. So concentrated nitric acid, heat strongly. Here there is formation of phosphoric acid. And so this is very important point to note that nitric acid is the only acid which can oxidize even the non-metals to form the corresponding oxidation product. So this is there. Now we are in the last segment of this video and we will see about the usage of nitric acid. So nitric acid, first as oxidizer in rocket fuels. This is very important point. It is used as oxidizer in rocket fuels. The rockets which fly high, they have the fuel, but there is no oxygen in the atmosphere. So it requires nitric acid. And nitric acid is cheapest way to have this. Now in processing of metals, when the metals are prepared, cleaning of metals, any metals, then in refining of gold, silver, it is in the refining, it is refining. Then in preparation of explosive like TNT, toluene, when there is, this is toluene, and there is the NO2, This is explosive, dynamite, TNT. This TNT, it is absorbed on Kisilgar earth. Kisilgar earth, it is a special type of soil. So it is dynamite. TNT is not active, but TNT becomes active when it is absorbed on porous material and it is Kisilgar earth. Then in preparation of TNG, trinitroglycerin, trinitroglycerin, so they are explosive. Then in preparation of fertilizers, nitrates, rather nitrate fertilizers, nitrates, all the nitrates, they are source of nitrogen. And so this is a very important point. There are different points, like etching of glass. You might have seen the written work is done using. So etching of glass etching is also there. So this is all about the nitric acid. Now one more point related to nitric acid is the chemistry of ring test. Ring test, it is used to confirm the presence of NO3 in a salt. Nitrates are confirmed, and nitrates, they give rise to NO2. Nitrates give rise to NO2, and so when the nitrate ions, nitrate salt, aqueous salt solution. So here I write down the salt solution of any nitrate. Then there is the concentrated sulfuric acid. Concentrated sulfuric acid. And here we mix freshly prepared FSO4. This is one, this is second. And here, now as a result of this, there is formation of this compound. This is penta, eco, nitrosyl, iron, second, sulfate. This is there. So what to do? In this, we take a test tube, and the test tube is basically bent. We keep like this. Test tube is slightly bent, and this test tube has the solution, base solution, freshly prepared ferrous sulfate, and then this salt solution. They are added in equal amount in this. So here this is the solution. Now with a dropper, we pour here concentrated sulfuric acid just inside. Sulfuric acid is very heavy. So what happens? It descends down. It moves down here in this manner, and it comes upward. So as a result, what happens? There is the formation of different layers. This is sulfate ion, ferrous ions, nitrate ions. So sulfuric acid it is pure. We are taking, and it is colorless. So initially there will be two layers. Here. First layer, this is the concentrated H2SO4 layer, and upper will be this slightly yellow colored solution or light yellow colored solution. But here there will be the dark browning. There will be this browning of this compound. This compound, it has dark brown color. If we draw here like this in test tube, so we'll have this type of condition. And see here, we have this type of condition. here there will be the this dark brown, and this concentrated sulfuric acid is here, and the mixture solution will be on the top. So this is called as chemistry of ring test. Chemistry of ring test. This is one point. Another point is why we take freshly prepared ferrous sulfate, because ferrous iron plus 2 is highly unstable and it is converted to Fe3. So Fe2 is converted to Fe3 by the loss of electron, and here it is light green, and here it becomes brown. Fe3 is brown. So as a result, it is advised to use always freshly prepared ferrous sulfate solution, because ferrous is oxidized to ferric, and so there can be some problem. And so this is about the complete explanation of nitric acid.